Okay, so now we have the prediction of the hydrodynamics slide of the suspended particles.
Thank you very much. Good afternoon. As you can see, my talk is about predicting the hydrodynamics in slightly wet suspended particles. I was expecting to see some work in this area, and I haven't seen any work in slightly wet particles, which are quite important in process industry. I'm coming from chemical engineering background, where we have, in many processes, particles are slightly wet and suspended. I'll show you some examples of what process I'm talking about. My first attention to this problem is when I was doing my PhD 5 years ago. I did look at bubbling fluidized bed where the particles were slightly wet. I added few drops of liquid, silicone oil, to a suspended glass beads in a bubbling fluidized bed. For those who do not know about the bubbling fluidized bed, I'll show you in the next slide what do I mean. But before I go to this one, look at the critical effect of very few drops of liquid on the flow hydrodynamics in a bubbling fluidized bed. What you are looking at here is tomographic images of bubble propagation in a bubbling fluidized bed of glass beads. You see here very clear the blue color is bubbles and the red color is the particles. I gradually added liquid, very few drops. What I'm talking about is around 3 milliliters or 4 milliliters of silicone oil in a 3 kilograms bed of particles, and then I fluidize it. What I have observed at the very small, very few drops, bubble splitting. This has never been reported in the literature before. Liquid tend to split the bubbles, and as you can see, these are the walls, and these are slice images using a tomographic imaging system. Further increase in the liquid, I've seen developing of sludging behavior. Another further very few drops of liquid, the bed started to defluidize, solid sludging, severe degradation of the fluidization quality. So we have a real problem here which hasn't been addressed. And I looked in the literature to see what available models can we use to simulate this case. I only found one paper in 2000 which is for discrete element modeling for simulating this behavior. Discrete element modeling, as we all know, time consuming, especially for this size of process. The other option is two fluid models. I looked for this type of model, and that can be used for simulating this case, which I haven't seen in the literature. And this is what I'm going to talk about in the next slides. If you are interested to know the tomography, just for curiosity, this is tomographic images, time 100 frames per second in a cross-section in the fluidized bed. And the blue color, as I said, is the bubbles, and the red color is the particle. And this is a very powerful tool for looking at the hydrodynamics in a fluidized bed.
Which liquid rates are we at?
The red color is the...
No, which curve on the left?
This is for dry case. this is just for the dry case.
Right. Okay,
Yeah.
thanks. Thank you.
For also, if you would like to know about the fluidized bed quickly, this is the fluidized bed I used in the experiments. And this here is the sensor. It's a twin plane sensor connected to a computer. And then you fluidize the bed. I added few drops of liquid from the top and leave it for around 30 minutes to get uniform distribution of the liquid within the bed, and then take my recording. Because I'm a chemical engineer, I'm interested in studying this problem because it is related to a lot of chemical engineering processes. These are some few examples. Liquid, very slight few drops of liquid in bubbling fluidized bed can cause sludging, as I have shown in the previous slide, and degradation of the fluidization. Another industrial case where we have moisture in the particles is in combustion and gasification of biomass. These are the situations where we have few drops of liquid in bed or in particles. In pneumatic conveying, we may encounter slightly wet particles in a conveyor. In fluidized bed coating, we spray liquid in order to coat the particles. This is another case where we have slightly wet particles. There is also a case of exothermic reaction where we spray water to control the temperature in the bed. So these are the situations where this process may occur. Then I thought about what could be going on between particles in this situation. Imagine we have two particles covered with a liquid layer. Then with increasing the solid fraction, at this stage here, we have collisions dominated by dissipation of energy due to increased inelasticity as a result of the liquid. There is another stage where we have slightly dense, or let's say call it dense intermediate, where the particles get in touch through a liquid bridge. And that is what I am imagining here. Then the last stage, at highly dense particles, where the particle get in direct touch with each other, the liquid is completely squeezed out, and we have a friction dominated contacts. These are just hypotheses, and I don't have the mean of experimental confirmation of this, but I did some few things. I took the particles, wet it, and then put it as loose packing under the microscope, and I looked at it. And it is true, particles, they really contact each other by a liquid bridge. These are 350 microns glass beads with the silicone oil. So we have a situation where we have a liquid bridge like this. Then in order to model a bubbling fluidized bed using the two-fluid model, this is the classic formulations of the two-fluid model: momentum, continuity, and energy equation. And you can see I am putting a circle here around the stress or the forces between the particles, and I'm also putting circle around the energy dissipation, and this term is the diffusion. So these are the two terms I try to modify in order to take into consideration the effect of these droplets of liquids. This is the shear stress and this is the solid pressure. And the question I'm putting here, can we extend this to include the effect of the liquid? Then I propose this modified shear stress model. We all know about the friction stresses and the kinetic stresses, or the apparent viscosity and the friction viscosity, and I included the wet, effective wet viscosity. And this is the classic soil mechanics principles for particles in friction. And the parameters here is the pressure, the internal angle of friction, the shear magnitude of the shear rate, and this is the situation where we can describe the particle pressure. We have a point where this really occurs at a critical solid fraction. Then we have the kinetic theory formulations for the solid stresses, widely used and very well known. The density of the particles, solid fraction, granular temperature, which describe the internal microscopic interaction between particles, velocity fluctuations. This is the restitution coefficient. This is the radial distribution function. And that's the kinetic theory description in the highly rapid flow. So these are the two extremes, and this is where the liquid is introduced here. Can we predict the liquid stresses at the bridge? Now, I went into the particle-particle at the particle-particle level interaction. There is plenty of work in this area, and the forces between particles in this situation are very well studied. And this is the forces can be simulated by this formula. This is the liquid viscosity. This is the relative approach velocity between particles. This is the gap between the particles, or the bridge gap. Now, in order to get the stress as a result of this one in an assembly, we need to know the number of particles, and I express this one in terms of the number of particles per unit area to get the stress. For this, we got the force per unit area. Multiply the term by the number of particles raised to power 2/3 to give us the number of particles per unit area. Then we have an approximation for the interparticle velocity, or the fluctuating velocity, from the granular theory, granular kinetic theory, where the velocity, relative velocity between particles, is estimated in terms of the granular temperature. Putting this term in the equation here, we end up with this equation. Now, this is the tricky part of my analysis. I treated this situation where the particles are in contact through the liquid bridge as if they are in friction through the liquid bridge. So I use the same analogy to put a lubrication coefficient, as you can see here, and the particle friction through this term. And further simplification of the problem, I took the angle of stability as if I am treating this one as in friction. There is some work done on this, on the angle of maximum angle of stability in wet particles, and they reported this angle to be between 20 and 40. For the range of liquid I'm talking about, it is somewhere here. The angle, this is a case, one case reported in this reference, and the angle of maximum angle of stability is somewhere between, around 30. Then in the same analogy also in friction, we need to find a point where this liquid bridge is breaking. There is some point where the liquid bridges become unimportant when they break down between the particles. So I needed to find the criteria for where these liquid bridges are really effective. Then I went and I did the same analysis as in the friction case, where we have a point where the liquid rupture occur, and in this case there is no forces between particles, and then there is a range between the rupture point and when the particle get really in contact. When the particle get in contact, usually they are not perfect spheres. So the sphericity of the particle is used here as H0. So between the liquid bridge rupture and the point where they contact through the sphericity is where the liquid bridges become important here. Now, there is one thing left, which is the interparticle gap distance in the fluidized particle or suspended particles. We need actually to relate H to the solid fraction or the concentration of the particles when they break. So I went into the literature and I found this. This is the expression for the liquid rupture. Once we know how much is the liquid per particle, we can estimate the liquid rupture, the distance where the liquid rupture. And for slightly wet particles, this gives the rupture. And if we know the mass of the liquid in the bed, we can know the mass of the liquid per particle. Then we can estimate the rupture using this equation. Particle sphericity, specifically talking in glass beads, for example, is somewhere between 2 to 10 microns. So it's a parameter that you need to input in the model to see the last range of the liquid bridge when the friction becomes important. Now, we needed an equation to relate the interparticle gap distance with the concentration. Then I went into the literature and I found this equation which relates the interparticle distance related to the solid fraction. So this is the solid fraction, and this is the equation which gives you the interparticle gap distance. So once we know the rupture point, we can relate this to the solid fraction by this way. This is an example for 150 micron particle with slight liquid, and the rupture is around 15 microns, and the other range where they get into contact through the sphericity is 5 microns. So approximately, this is the range where the interparticle bridges are dominant here. Now, the last thing I wanted to look at in the rapid flow, I assume that the liquid bridges or the liquid effect is directly can be represented by the restitution coefficient. As a result of the liquid, we have increased in elasticity, and if we can find the restitution coefficient for this case, then we can simulate the dissipation of energy in that rapid flow. Fortunately, there is a quite a number of work in the restitution coefficient for the case of wet particles, and these are some examples here. Taking the restitution coefficient as function of the Stokes number, it makes up the solution of the problem complicated. So I went into a simple method where I express the restitution coefficient in terms of the sphericity and the gap or the liquid level in the particle. Now I went into the solution of the equations, the model equations. I put it in algebraic equations, and I solve it using numerical methods to simulate the flow system in a very simple one-dimensional flow in a horizontal duct. This is an example of the results, just one simple example. And where we can see this is the kinetic stresses. This is the stresses due to the liquid, and this is the stresses due to friction. And as we can see, they tend to match and provide a smooth transition for the case of liquid bridges here. This is the flow map for the case of dry and wet. And as we can see, we have a change in the behavior where the curve tends to the left and then move to the right here due to the increased dissipation here and due to the liquid bridges towards the dense flow. These are few hydrodynamic description of the solid fraction for the wet and dry case. Whether this is the good prediction or not, we need to do some experiments to confirm this, which I haven't done yet. This is also an example of the solid velocity, which shows that the velocity decreases somewhere in the wet region here, where the particles are dense in the lower region, and it is higher here. And this is something I need to confirm with the experiments. This is the granular temperature profile, where in dry case we have this granular temperature. It is high at the middle because of the high collisions, and low at the walls because of low collisions. And this is the case for the wet. These are comparison between the liquid stresses and the kinetic theory predictions. As we can see, the liquid stresses at the bottom, where there is a high dense particle due to contact with liquid bridges, it is somewhere very high at almost 5 times greater than the dry case. And this is the energy dissipation. As we can see, higher dissipation in the case of wet flow. This is my conclusion, and thank you very much for listening.
Any questions?
You showed very neatly the formation of your liquid bridges under the microscope there. Can you tell me how much volume flow of liquid from the separated particles goes into that, forming that neck? Because if there's a substantial amount, then presumably the viscosity of the liquid can play an important part.
You mean how much volume of liquid per particle?
Yeah.
It's very small compared to the particle volume.
Sure.
And it is percentage 0.01% of the particle
You
volume.
have a film of liquid around the particles when they separate. How much of that film has to flow into the neck region to form the liquid bridge?
Virtually nothing.
Okay.
I have a general question about this approach where you separate between the frictional and collisional stresses, and especially in the pressure, granular pressure that you take as a function of the porosity. You have this, I think it was the second slide, that you have this A parameter. The granular pressure is a function of the volume fraction. Just the two-phase flow model, yeah.
Yeah.
And now the slide after. Yeah,
Okay.
here. You have the pressure or the frictional part of the stress, which is a function, but you have this A, capital A,
Yes.
which from a dimensional point of view is a stress. Could you comment on what is the stress scale that should be here?
Well, these are unfortunately arbitrary parameters which really require experimental validation. This is a hypothetical model, and the values are arbitrary, and usually even the switching point is arbitrary. So I have no comments on this because this is available in the literature and people are using it for simulating the friction case. So these are arbitrary values.